All right, this is a guide to solve weekly project number 7, rock failure and application to wellbore stability. The first exercise is about the determination of the shear failure parameters and also the tensile strength for Darley-Dale sandstone with results of triaxial strength measured in the book of Jaeger, Fundamentals of Rock Mechanics. Basically, what you have over here is a set of experiments conducted at different pore pressures in which at different confinements to S3, we have the values of the maximum total axial stress, the values at failure. And what you have to do in order to process this data is for each of these experiments that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. For each point is an experiment. For those 14 experiments, you have to rewrite this plot or replot this data in terms of effective axial stress sigma 1 on the y-axis and effective axial stress, effective radial stress sigma 3 on the x-axis. When you do that, you're going to be able to fit a law that could be, for example, the Mohr-Coulomb failure criterion. That should look something similar to this, but now you're going to have 14 points. Let me tell you something that probably you could use when you do this. Usually, what we see is that the Mohr-Coulomb is just a linear approximation. And in real rocks, we tend to see that the sigma 1 tends to decrease and not follow the trend or at low mean stress. At high mean stress, it tends to deviate. And you may see something similar in your data. And if you do that, if you see that at very high values of sigma 3, some of your points are not in the trend, then rather than forcing your data to fall onto that line, you may just ignore those points and say that your parameters are valid for a given range of sigma 3. If you want to get something that fits the entire data well, then you will have to use something else, like, for example, the Hooke-Brown criterion, but we haven't seen that. So don't worry, I'll prefer that you fit a line and the Mohr-Coulomb criterion to the region in which the model describes well the data. All right, so basically this is what you have to do. Then obtain the parameters UCS and Q. And as soon as you have those, you can calculate what is the cohesive strength and the friction angle from these equations over here. Let me get in there. These two equations are going to help you obtain the cohesive strength and the friction coefficient that is going to be later on you can convert it to the friction angle. And the point number 3 or C is that you also can calculate the parameters for the Drucker-Prager criterion. And basically what you have to do is with the same data that you have, instead of fitting a parameter or a yield surface to principal stresses, you do that in terms of the stress invariants, I1 and J2. So it's the same procedure. From there, you're going to get coefficients that fit the Drucker-Prager criterion. And with that, you're going to have your yield surface. So very similar to the one before, but just with a slightly different approach with I1 and J2. And the last point asks to compute or calculate or estimate the tensile strength of this same rock, assuming relationships that are given in Jaeger's book. If you check Jaeger's book, if you go to the part of tensile strength, you will see that many times you can relate the tensile strength to the value of UCS or to the value of the cohesive strength. So please do a little bit of literature review and find that value because you're going to need it in the second problem. The second problem is about the calculation of shear failure and tensile failure in deviated wellbores. For this topic, what you're going to have to do is to compute stresses around the wellbore for a wellbore at an arbitrary deviation. And in this case, all the math that you need in order to calculate those stresses is right here. And once you have your stress tensor in the principal stress coordinate, then you can project that. I'll come back to this in a sec. You can project that into the coordinate system of the wellbore. And once you have that coordinate system within in the wellbore, which is going to look like this, then with these equations, which is the extended Kirsch equation to consider also shear in the far field, sigma 1, 2, which is going to come from over there, you can calculate all the stresses around the wellbore. And there is one more step over here. Now you do have a shear stress in the direction theta z. Notice this is not a shear stress in direction rc or r theta because that's not possible to have. The math cannot apply a shear stress in that direction, but you do have one now in the direction tau theta z. So because of that, now you need to calculate your principal stresses at the wall of the wellbore. And in general, that's not going to coincide with the axis of the wellbore. Your principal stress is not going to be the hoop stress anymore. Before it was, but now it's not going to be like that. And it's going to be a little bit deviated in general from the direction of the axis. How you find that principal stress? Well, you find it by calculating the eigenvalues. You can either calculate the eigenvalues or you can use this equation, which is calculates the principal values for just a matrix 2 by 2. And once you have your maximum stress and your minimum effective stress, both principal stresses at the wellbore of the wall, and notice that it's not the hoop stress anymore, and also you have the axial stress in there and the shear stress. After you do that, you can check whether the Mohr circle is going beyond the shear failure or if the least principal stress is going lower than the tensile strength value, which is this little blue line over there. So that's the workflow, and it is very similar to what I have in this Python script, which I will share in a minute. Let me see. I was meant to come back over here. And we'll see how our solution is going to expand to this type of plot. All right. So you're going to have to provide your solution not for one wellbore, but for all the possible wellbore orientations in the lower hemisphere projection, which looks like this, where this lower hemisphere projection tell you what is the azimuth and deviation of a wellbore, and they respond to this convention that we have over here. In this convention, we can isolate a given section of the wellbore. Notice this is not the wellbore, okay? This is just a section or a segment along the wellbore, and any segment along a wellbore is going to be a line in 3 dimensions, and you can characterize it by 2 angles. the azimuth, and the deviation. And you can plot that three-dimensional orientation in these lower hemisphere projections where the deviation goes from 0 to 90 from the center to the edge of this circle, and the azimuth goes from 0 to 360 degrees, where the azimuth is the angle between the projection of this line on the horizontal plane. Notice that opposite to faults, here what we are plotting in the lower hemisphere projection is exactly the point in which this segment is hitting the lower hemisphere projection. So it's a little, in that sense, it's a little bit easier to understand than the faults, because the faults, the pole is not giving you actually direction of the fault, but it's giving the opposite. And it doesn't tell you the strike directly either, but it is the perpendicular direction. Well, in this case for the wellbores, it is exactly that. So this is one possible orientation of a wellbore. In the solution that you have to provide, you have to, let me close this, you have to provide the solutions for all the possible orientations. And your results are going to look more or less like this when you plot that solution for all possible solutions and with, for example, with colors in this case. Why we do this type of solutions? Because you can overlay on top of those solutions your wellbore deviation survey. If your wellbore, for example, this is a real deviation survey, in this case is coded with color by depth, showing that the wellbore starts here and as it goes into deeper and deeper, it gets more vertical. But we can track the wellbore trajectory in this type of lower hemisphere projections. For example, here, if we had a wellbore that starts vertically, it will be somewhere over here. And let's say that it is a wellbore in the Permian, which is going in direction south. And it goes south as it goes horizontal. Then the wellbore trajectory is going to start here, and we're going to have points as we move along that direction. I'm trying to bring my annotation tool in here. Okay, so it will start there, and then segments of the wellbore will move along this direction as we go eventually into a horizontal wellbore right there. And combining these plots of the solution of wellbore stability with the trajectory of the wellbore, we can tell if we're going into trouble or not. So this is what you're going to have to do. So let me tell you in general how the workflow is going to be. Let me delete this and then I'll continue. All right. What I propose that you do in order to solve this problem is first to have a script that solves a wellbore stability problem at the given deviation. For example, in this case, I'm solving the wellbore stability problem for a vertical wellbore, in which if I run this code, what I see are the hoop stress and the radial stress for given parameters of SH max, SH min, pressure in the wellbore, pore pressure, and also constitutive parameters or properties of the rock, such as tensile strength, UCS, and the friction parameter Q. By coding the equations of Kirsch, and later by checking if I have a tensile of a shear failure all around the wellbore, what I can do is I can check where there are regions of shear failure or tensile failure. In this case, for example, what the solution is telling me is that I have more or less a breakout angle of 40 degrees in these sections. Why? Because I have shear failure from theta equal to more or less 70 to theta equal to 110. So that's going to be a breakout angle of 40 degrees in this at this location, and another 40 degrees at this location, but the breakout angle is 40 degrees. If, for example, I were to change the variables here and have more stress anisotropy, the breakout angle would increase. So your solution can tell you what that breakout angle is and export that as a solution for a particular wellbore. Okay, for tensile strength is the same. If I were to, for example, here increase the wellbore pressure, okay, I was lucky I ran into a point in which I have no failure at all, but let me increase that a little bit more. And still no failure. And now, because I have increased too much the wellbore pressure, I start to have tensile failure. So your code can track both. For a given condition, what is, if you do have a shear failure, what is the breakout angle? And if you have a tensile failure, if there is or not a tensile failure. And what you're going to have to do is to put all this script and this logic into additional two nested for loops, where one for loop is going to expand what happens when, for example, you change the deviation. The solution that I share with you over here is just for a vertical wellbore. So it will give me the answers I'm looking for just this wellbore. But I could create a for loop that explores from deviation from 0 to 90, and let's say in intervals of 1 degree. So by varying the deviation, I could also obtain a solution at azimuth equal to 0 and deviation 0, 1, 2, 3, 4, and so on until 90 degrees. So now I'm going to have 90 solutions. And I can put now those two scripts within another for loop that explores the azimuth. And I can change that azimuth also from 0 to 90 degrees. And by doing that, I'm going to have, let's say that I'm going to have 90 solutions in this direction and 90 in this one. So I'm going to have 3,600 solutions that are going to fill all of these quadrant and are going to allow me to do a surface plot like the one over here for this part of the solution. Notice that the solution is going to be symmetric. So probably instead of using 360 degrees, if you want, just go until 180, and then by symmetry, you can get the other part. But today, you know, computers are so powerful that you just can go 360 degrees, and then your solution space is going to be 90 times 360. And once you have that surface solution, you can plot it similarly to what we see over here, in which what we have is the solution now expanded to different stress regimes: normal, strike, slip, and reverse. And please use also this solution. Let me get the reference in there. Please use this solution to compare your solution, and it should look similar to this. Just notice that your color map by default is not going to be the same as this color map over here. So it's not going to be look exactly the same unless you have the exact same color map. But it's going to look more or less similar to this one. And that's basically everything you have to do. And in this problem, first you're going to start with the Mohr-Coulomb criterion, that with the properties that you found for the rock that you have in exercise number 2. And then I'm asking you to extend that for the Drucker-Prager criterion and also for the modified Ley criterion. And once you have that, if you have the script that solves stresses around the wellbore and you have your constitutive properties, that's everything you need. Again, if you need a little bit of help with this part of wellbore stability, I recommend that you check this link. Well, this is not actually the link, but I'm going to send you the link. I'm going to post a link in my notes. And the only thing you have to do is to put this within two for loops, one that explores deviation, the other one that explores azimuth, and then you can get the solution.